the eccentric load P is equivalent to an axial load P and a moment PE, as shown by the side diagrams to the right of the short column. Then the axial load P will give an axial direct stress P over A. The bending moment PE will give us a bending stress M equals sigma Z. The combined stress diagram can take one of three different forms as shown on the book. The basic formula is MOI equals sigma y. Sigma is maximum when y is maximum. Then MOI equals sigma maximum or y maximum. Therefore, sigma maximum equals M I over y maximum equals MZ. Therefore, Z equals I over I maximum. The bending formula can be written as MOI equals sigma over y or M equals sigma Z. However, when using M equals sigma Z, we must know that sigma is the maximum value of the bending stress. We have to draw the combined stress diagram. The eccentric load 12 kN is equivalent to an axial load 12 kN and a moment 7.2 kN. We may write the combined stress as equal to M equals sigma Z, MOZ. Z equals 1/6 is 1. Now, example 2 is given on the board. Before considering this, I want to explain to you 2 points which we have been talking with regard to these problems. One is short columns. We are considering only short columns. If we use long columns, they will buckle and all our theory is not applicable. Second point, we have been always asking for the stressors at the base. This is because the maximum stresses occur at the base. With regard to this problem, you see there is no vertical load given. In all the problems we considered before, we had a vertical load, and we did not consider the weight of the column, because we assumed that the vertical load applied is much greater than the weight of the column. Now in this problem there is no external vertical load applied, and therefore under the force P, the column will rotate clockwise and break down. Therefore we have to consider the weight of the column as the vertical load. The weight of the column is that which resists the rotation of the column under force P. Therefore, the weight of the column is the direct stress this direct stress could have been more easily calculated by just multiplying the unit weight of the column material by its height. Then direct stress equals 20 into 3. So whenever we do these problems, we don't have to calculate like this. We just multiply the unit weight of the material by height. You will notice that we use the plus sign for compressive stresses, because in columns the major stress is the direct stress, which is compressive. The example 2 is given on the board. The load P is acting at the midpoint of the top left-hand edge normal to the face of the column. Then the direct stress sigma D equals 5 into 20. Here, direct stress sigma D is given here, bending stress sigma B is given here, and the final stress is the addition of the direct stress and bending stress, which is given at the bottom as sigma C, the combined stress sigma C. Yes, example 3 is given on the board. where a uniform wind pressure is acting normal to one face of a brick wall. The direct stress sigma D equals 3 into 22 equals 66. The moment above the base equals 2 into 3 into 1 into 1.5 equals 9 kilonewton meters. Z equals Vd squared over 6 equals 0.24 meter cube. The bending stress sigma B equals plus or minus m over z, which is equal to plus or minus 37.5 kilonewtons per meter square. And the combined stress is shown on the board.